Hello. We've seen our Mercury dataset for quite some time, and what I'd like to do now is to formalize one of these bullet points that we've seen in the past. So I would like to tackle a little bit statistics to confirm the answer. To do so, we need the concept of a statistical model. A statistical model is linking my observations with random variables in a somewhat formal way, in a mathematical way, with respect to an equation, say. And we will use that formalism then to quantify our answers in a statistical manner. So say statistical model 1. And let's denote my observations as yi. Those are the observations. And probably one of the most simplest model is to write those observations as random variables driven by some mean mu and noise epsilon I. So here we would have the mean, and here we would have noise or measurement error. And pragmatic, typical assumption is that my noise is what we call IID, independent and identically distributed according to a normal distribution with mean 0 and variance sigma squared. Okay. So what could this model be used for? Well, we could have a look and test if the mean of my observations, the average, deviates from some hypothesized mean. Or we could, for example, compare the mercury content in Lake Geneva from 2 different years and see whether there was a significant improvement over the years or whether the situation has worsened. And that's probably what I'll show you next. So maybe we could write here as yi, so in the year 78, and yi in the year 83, and then compare if there was some improvement over the years. I would like a formal way to confirm this answer. Okay, now we're going to look at this formal test procedure, say what we call statistical modeling part 1 with R. We have here several data files concerned with mercury content of Lake Geneva. This was the original one. Here I'll have one containing the 2 years, years 78 and 83, and here one from 88. Okay. I'll have an OpenR Studio here. I'll just resize everything to what I need and open a new script. So statistical model in part 1, say testing. Formal, simple t-test. First, we read in our data set. So we put everything into, say, the variable dot read, comma, separated value of, and how was that file called? That file was called lemon hg underscore 78 underscore 83 dot comma separated value. I think it was that. Let's quickly test. It went through, so I presume everything is okay. Quick sanity check whether we actually do have the data, whether the data is in correct format. Check data. So first, maybe what is that? Okay, so does it have a dimension? I want to see the structure of it and maybe a short summary. Okay. First, the dimension. Yes. So apparently we have 294 observations, 4 variables, reflected here. Let me slightly increase this. Okay. Yeah. So you can see the same numbers here, of course. X, Y, those will be then the location, and 2 variables, mercury content 78 and 83. And summary. Okay, we don't see any issues with respect to not availables, all positive values. That's a good sign. Let us quickly plot the values. Let's start with locations. Okay, I will move my image up there, and we do recognize again Lake Geneva here. What else do we see? Let's plot the histogram of the values in 78. There it is. Naturally, I can copy this line to reproduce the same for 83. Okay. If I go over here into this part of my RStudio panel, I can now go back and forth and compare those. It seems that the 78 values are slightly higher. Huh? They go above 2. 83, they're all virtually all below 1.5. Okay, so could I compare the 2 histograms, superimpose? Well, I think, let's see what happens if I add here color equals 7. So I would plot, get yellow there, and add true. So I'm going to add this to the existing plot, and we would see that, yes, all this part here is excess of in 83. Sanity check. That was sanity check. Okay, let's make a new variable called change. This change would then be, say, the values of 78 minus the value of 83. That means positive values mean a decrease over time. Negative values would mean an increase. How does that change variable look like? Again, so here define variable containing the difference. Okay, so in some sense positive is good. Okay. Summary change. What do we see? Yes, we do have negative values, we do have positive values, but it seems that many values are positive. Slightly positive, but positive. The histogram of change looks as follows. Yes, okay, we do see majority positive. Probably a few more bins would be suitable. Yes, yeah. So a few very large values, but everything else is okay. Okay, the mean of change is what? Will be positive, will be small. How small? 0.32. That's positive, small. But does this small value mean that we actually do have a significant change? A change that is significantly positive? Can we say there is a significant improvement of the quality in the sediment, at least with respect to mercury? Well, for that we would have to use this t-test. We test whether the variable change is its mean is significantly greater than 0. The command to do so is called t.test, and we just have to insert the variable change. Okay, this is the output. So we've performed a one sample t-test based on the variable change. This is the t-statistic, the degrees of freedom, and the p-value. This p-value is extremely small. That means we can reject the null hypothesis that the true mean is equal to 0. Hence, there is evidence that we have actually a decrease in the mercury levels. Note here that I also get a confidence interval of the mean, and this is roughly 0.27 and 0.26, and the mean of the sample is of course in the center of these two bounds. So that is for the samples between 78 and 83. Now let's look at the third time frame that we have at our disposition. This is with respect to the year 88. We have again a data set, so we're going to read the data set. And again, using the command read, comma, separated value, and this is then Lehman Hog 88 CV. Let's test. It is apparently there. What do we see there? The structure of that 88. And we see that all of a sudden we have only 201 observation only. Recall that we had virtually 300 for the 2 other 10 stems. Well, that's not very good news, in the sense that now we cannot really take differences. We cannot take a difference between a vector of length almost 300 and one almost 200. That does not work. Let's maybe quickly have a look what happens. Okay, what happened to or what's going on with respect to the locations. I'm going to plot again the locations that we had until now. Those are the locations. Now I'm going to superimpose the new ones. $x dot $88 In order to make them visible, I'll choose a different color, say red, and I slightly decrease the point size, say 0.9, and that happens. Okay. So they did not take all the same locations. They took virtually the same grid as before, but here in the center, that's actually where the lake is very deep, they did not take as many samples. They have some particular samples what seems outside the lake, here, 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 and here. To be honest, I presume we have recording errors here. This should be over here, this should be over here, and this is actually this location and this location. Whether that's possible or not, I don't know. You could, for example, test that and compare whether those are actually still within a lake boundary, probably not here, or within a river, probably not here either. For the moment, let's assume that the remaining part of the data set is clean. We won't use the location for this analysis, hence we don't have to worry about this small discrepancy. However, we cannot, as mentioned, we cannot use the one sample t-test, which would actually also be a paired two sample t-test. So we use here a two sample t-test. So t-test, and then I'll specify the two samples, that 88 mercury and that mercury of 83. I think that should be sufficient. I can launch, and what I do see now is, oh no, now we do not have evidence to claim that there is a difference between the two sample means. Very large p-value, two means are very close. So it seems that, at least given the two samples, that the average mercury content remained stable within those 5 years. As a small add-on, you could maybe try and to evaluate what is exactly different with respect to the third Lehman data set. Recall that we would have a third one, read Lehman, okay, comma, separated value, okay. Compare that to the other ones that we've seen in this short video, and try to explain what is actually going on and why do we have all of a sudden now 3 data sets.